floating point unit is developed to speed up calculations on real numbers encoded in a computer as floating point numbers. At the beginning of the x86 processor's history, the FPU was a separate integrated circuit. Since the i486DX processor, it has been introduced as a standard element of each processor. Because it was a separate unit, it is often called the math coprocessor. The FPU operates on single, double, or extended precision values using its own set of registers and instructions. Registers in the FPU are organized as a stack with 8 levels of depth. Physical registers are named R0 up to R8, while registers visible by the FPU take names ST0 to ST7. The ST0, also referred to as ST, is always the top of the stack, while ST7 is the bottom of a stack. The top of a stack is pointed to with 3 bits in the FPU status word register. Each time the data is loaded to the FPU, the stack top is decremented, and each time the data is popped off the stack, it is incremented. The stack organization of registers makes it easier to implement math calculations according to RPN, reverse Polish notation, also called postfix notation. The FPU coprocessor's instructions can be grouped in following groups: data transfer instructions, load constants instructions, basic arithmetic instructions, comparison instructions, transcendental instructions, and FPU control instructions. Data in the memory used by FPU can be stored as a single precision, double precision, or double extended precision floating point value, or as an integer of the type word, double word, quad word, or 18-digit BCD number. The FPU always converts it into double extended precision floating point while loading it into an internal register, and converts the data to the required format while storing it back into memory. Loading instructions always first decrement the stack top in the status word, and next load the value onto the new top of the register stack. We have 3 load data instructions. They have only one argument. The FLD instruction loads a single precision, double precision, or double extended precision onto the FPU register stack. It can also copy data from other FPU register into stack top. The FILD instruction loads integer values of word, double word, or quad word. The FBLD instruction loads an 80-digit binary decimal encoded value. Store instructions take data off the FPU register stack and place it in the memory. The FST instruction stores a single precision or a double precision value to the memory. It can also copy a value to another FPU register. The FSTP instruction also works with 80-bit double extended precision values, and additionally pops data off the stack by incrementing the stack top field in the status word register. It can also copy a value to another FPU register, popping it off the FPU register stack. The FIST converts the value from the top of the FPU register stack into a word or double word integer and stores it in memory. The FISTP instruction can also store a 64-bit quad word integer and pop the value from the stack top. The FBSTP pops a value of the FPU register stack and writes it in an 80-bit BCD encoded integer in memory. I think you noticed that there aren't instructions to copy values from the FPU register to general purpose register. It is also not possible to load the constant encoded as an immediate value, but some constant values can be pushed onto the FPU register stack. You can load 0, 1, pi, and results of some logarithmic equations, log to the base 2 of exponential constant e, log to the base 2 of 10, log to the base 10 of 2, and log to the base e of 2. FPU is created to perform calculations, so it implements an extensive set of mathematical instructions. Basic arithmetic instructions group contains addition, subtraction, multiplication, and division, available in various versions. Arguments of these instructions determine their behavior. Let's consider an example of subtracting. All other calculations behave the same way. If the instruction has a single argument, it must be a memory argument, which specifies a single precision or a double precision floating point number. The result is always stored in ST0. The version with two arguments work with registers only. The order of arguments determines the order of the calculation and result placement. For example, f sub st0 sti subtracts sti from st0 and stores the result back in st0. The f sub sti st0 subtracts st0 from sti and stores the result in sti. The popped version with two arguments additionally pops the stack. For example, f sub p sti st0 subtracts st0 from sti, stores the result in sti, and pops the stack. It is also a no-argument version available, which implies st1 as the destination and st0 as the source argument. For example, f sub p subtracts st0 from st1, stores the result and st1, and pops the stack. The result is then at the stack top. The addition and multiplication operations are commutative, while subtraction and division are not. That's why the reversed versions of subtraction and division are implemented. The difference is the order of operations, while the destination remains the same as in non-reversed versions. The basic arithmetic instructions also contain instructions for other calculations, including the absolute value, rounding, sign change, and square root. It is possible to scale the value by a power of 2 and separate the number into mantissa and exponent. The comparison instructions compare two floating point values and set flags in the FPU status register appropriate to the result. The operand of the fcom instruction can be a memory operand or another FPU register. It is always compared with the top of the stack. If no operand is specified, it compares st0 and st1. Popped version of fcom-p pops st0 of the stack. The instruction fcom-pp with double p at the end can't have any argument. It compares st0 and st1 and pops both registers of the stack. There are also instructions to compare integers stored in memory to test if the st0 is 0, and instructions which set flags in the main CPU flags register. The transcendental instructions perform calculations of advanced mathematical functions. It is possible to calculate the sine, cosine, and tangent. The argument of all these instructions is st0, and it doesn't appear in the mnemonic. It is good to remember that there are some limitations in calculations. First, the results are approximated. Second, tangent is called partial, which means that this instruction handles only a limited range of input arguments. After calculating the tangent, the value of 1 is pushed onto the stack to make it easier to calculate cotangent afterwards by executing the fdiv-r instruction. Arcus tangent instruction, FPA results the angle between the x-axis and the line from the origin to the point x and y, where y, the ordinate, is in st1 and x, the abyssa, is in st0. It considers the sine of both components, returning the proper angle from all quadrants. There are also instructions to calculate exponential and logarithmic functions. The f2axm1 computes the exponential value of 2 to the power of the source, operand, minus 1. Operand and result are in st0. The fyl2x computes the logarithm base 2 of st0 and multiplies the result by st1. The fyl2xp1 computes the logarithm base 2 of st0 plus 1 and multiplies the result by st1. Result of both logarithmic instructions are returned in st0. The FPU control instructions help the programmer to save and restore the contents of chosen registers if there is a need to use them in an interrupt handler or inside a function. It is also possible to initialize the state of the FPU unit or clear errors. Although in modern processors there are new, faster vector floating point instructions implemented, the FPU, with its 80-bit encoded floating point numbers, is the unit that offers better precision of computations.